Okay, so sample problems using all of the formulas and all of the knowledge that we have acquired earlier. So in this sample problem, what is to be the angle in radians? So what angle in radians is subtended by an arc 3 meters in length on the circumference of a circle whose diameter is 12 meters. Also, what is to be its angle in degrees? Okay, so suppose that we would now be having a certain circle with a diameter 12 meters. So let's say that this is now to be 12 meters. So there is now to be an arc 3 meters in length. So if this is now to be the radius, so of course it would now be, let's say, turning here. So with that, this is now to be the subtended arc. So according to the problem, this arc is now to be 3 meters in length. So what is now to be its angle? So what is now to be its angle in radians? So this is now to be theta r. So basic. And as you can remember, theta r is to be equal to the arc subtended divided by the radius. So in here, we already have the arc subtended. And as for the radius, it is basically half the diameter. So if radius is basically half the diameter, so we can say that our radius is now to be equal to 6 meters. So half of 12. So 12 meters divided by 2, 6 meters. So with that, the angle in radians is equal to, so 3 meters divided by, so what is now to be the radius? So 6 meters. So 3 meters divided by 6, so that is basically 0.5. So proving it using the calculator to your left, so 3 divided by 6, 1 half, 0.5. So this is now to be equal to 0.5 radians or 1 half radian. Okay, so this is now to be our first answer. And we actually have a follow-up question here. So what is now to be its angle in degrees? So for its angle in degrees, so angle in degrees is basically equal to, so if this is now to be our angle in radians, so 0.5 radian. So we would just be multiplying this by our conversion factor of, so for every radian, there is to be a certain amount of degrees. And in that case, for every 360 degrees, there are to be 2 pi radians. So with that, looking at the calculator once again, so 0.5 radians, we would just be multiplying this by 360 degrees divided by 2 times pi. So 0.5 radians, 360 degrees divided by 2 pi. So with that, our angle here is now to be equal to 28.648 degrees. So this is now to be our answer for the follow-up question. So as per the problem at the bottom part, the angle between two radii of a circle of radius 2 meters is 0.6 rad. What length of arc is intercepted on the circumference of the circle by the two radii? So let's say that we would be having this particular radii here. So when we say radii, it is basically the plural of radius. Okay, so let's say that this is now to be our first radius. And let's say that this is now to be our second radius. So this is now to be 2 meters. And this is also 2 meters. So it is said here that the angle between them is now to be equal to 0.6 rad or 0.6 radian. Okay, so what is now to be the length of the arc intercepted by this particular radii? So this is now to be the subtended arc. So this is now to be the arc. So if this is now to be the arc, so arc is now to be S. And once again, we can say that the angle in radians is equal to S divided by R. So we already know the value for our radius, and we also know the value for our theta R. So for theta R, that is 0.6 rad. So 0.60 rad is equal to S. So we do not know that yet. So S divided by R. So our R is now to be 2 meters. So 2 meters. So solving for the value of S. So S is to be equal to, so cross multiplying. So multiply 2 meters by 0.6 rads. So 2 times 0.6. Our answer here is now to be equal to 1.2 meters. So this is now to be our final answer for this particular problem. Okay, so proceeding, let us have more examples. So third example. So what is now to be the angular velocity in radians per second of the crankshaft of an automobile engine that is rotating at 5,000 RPM. So when we say RPM basically means revolutions per minute, or in some cases rotations per minute. So what that basically means is that for every minute, the crankshaft rotates at, well, 5,000 rotations or revolutions. Anyway, so I do not know what a crankshaft is. What I know is that it is rotating. So that is what matters in this problem. Okay, so its rotation once again is now to be 5,000 RPM or revolutions per minute. So what we are going to do here is that we would just be converting these units in terms of radians and seconds. Okay, so the first thing that I want to do is for me to convert revs into radians. So I would just be multiplying this by our conversion factor of. So for every revolution, so for every rev, so that, there is now to be 2 pi radians. So why is that the case? Because earlier, I have said that for every 2 pi radians, there is now to be 360 degrees or 1 full rotation. And in this case, 1 full rotation is, well, synonymous to the term revolution in this problem. Okay, so for every revolution, there is once again 2 pi radians. So in that case, rev would now cancel out and we would now be arriving at a unit of radians per minute. However, in our problem, we want our answer to be in radians per second. So once again, we would now be multiplying this by another conversion factor that will cancel out minutes here. So in that case, so minutes should be at the denominator side this time, 4 minutes to cancel out. And I want my unit to be in terms of seconds. So seconds at the bottom part. So for every 1 minute, there is to be 60 seconds. So there. So as you can see for the units, so rev would cancel out, minute would cancel out, and you would leave us an answer in radians per second. Okay, so the next thing that I am going to do here is that I would now be using my calculator, of course. So 5,000 times 2 pi divided by 1 times 1 divided by 60. So that is now to be 500 over 3 pi. So 500 over 3 pi radians. So if you want your answer to be in terms of pi, so this is now to be the answer. But you know that pi is basically equal to 3.1416. So in other words, this is to be equal to, so if you would now be multiplying 3.1416 by 500 over 3, our answer here is now to be equal to 523.599 radians. So this is now to be our final answer. So both of these answers are basically the same. So radians per second, I should say. So per second, I forgot per second. So 523.599 radians per second. So this is now to be our final answer. Okay. So proceeding, it is said here in the problem that if the crankshaft in the previous problem decreased its angular velocity uniformly from 5,000 RPM to 1,000 RPM in 10 seconds, find the angular acceleration. Okay, so its speed initially is to be equal to 5,000 RPM and its speed after 10 seconds is now to be 1,000 RPM. So the first thing that I will be doing here is that I will be converting both of these first in terms of radians per second. So as for this first one, so I have already converted this earlier. It is to be this. So I would just be making use of this value here for my answer to be exact. So initial velocity So initial angular velocity is equal to 500 over 3 pi radians per second. And for our final velocity, so that is to be 1000 RPM. So I will be converting this first into rads per second. So 1000 revolutions per minute. So using this conversion factor here, times 2 pi rad divided by 1 rev times 1 minute, 60 seconds. So this would now cancel out and would give us an answer in. So looking at the calculator to your left, so 1000 times 2 pi divided by 60, and our answer here is now to be 100 over 3 pi rad per second. Once again, if you want to use its decimal equivalent, you can use 104.7198. But in today's video lecture, I would be using the whole fraction for my answer to be 100% accurate. So this is now to be WF. Okay. So, since we are to find the acceleration and acceleration in terms of rotation, that is now to be alpha. So alpha is equal to, so if you can remember from linear motion, that acceleration is to be equal to VF minus VI over 2. Or you can also make use of VF is equal to VI plus 80. And if you would now be simplifying this equation, you would still be arriving at this equation if you are solving for the value for A. Okay, so with that, so alpha is to be equal to, so omega final minus omega initial divided by T. Or, so once again, omega F is equal to omega I plus alpha T. So final velocity, initial velocity, acceleration. Both of these equations are to be the exact same thing. Okay, so with that, this is now to be equal to, so what is now to be our final velocity here? So 100 over 3 pi rad. And as for our initial, that is now to be 500 over 3 pi rad. So divided by what is now to be the time in seconds. So that is now to be 10 seconds. So I will just be rearranging this. So our answer here would now become, so looking at the calculator once again, so 100 over 3 times pi minus 500 over 3 times pi divided by 10 seconds. So our answer here is now to be equal to negative 40 over 3 pi radians per second squared. So by the way, this is now to be a rad per second, and this is also rad per second. And if you would now be simplifying the units, you would be arriving at a unit of radians per second squared. So radians per second squared. So this is equivalent to, so its decimal counterpart would be negative 41.888 radians per second squared. So this is now to be our decimal counterpart. And since it is negative, what this means is that this is to be a deceleration. However, since we are finding the acceleration, of course, it is now to be negative. However, if what is needed in the problem is to be, let's say, the deceleration, so your answer should be positive. So what is to be the angular deceleration of the object? So 41.88. So once again, this negative symbol here means that it is slowing down. So as you can see, this is faster than this, so it has slowed down to 1000 RPM. Thus, negative value. Okay, so there. Okay, so let us have the final problem for today's video. So in this case, so a car tire has a radius of 0.35 meters, and if the car accelerates in a straight line from rest at 3.15 meters per second, So basically guys, meters per second is equal to meters per second squared. So this is also equal to, so meters per second. So meters per second squared. Okay, so calculate for the angular acceleration of the front passenger tire. So let us list the given first. So given. So the car tire has a radius of 0.35 meters. So this is now to be the radius of the tire. Okay, so proceeding. So it is said here that the linear acceleration is to be 3.15 meters per second squared. Okay, so what is required in the problem is that of the angular acceleration. Okay, so for the solution, okay, so in here it is said here that the linear acceleration of the car with tire 0.35 meters is to be 3.15 meters per second squared. So how can we convert this into angular acceleration? Okay, so let's go back to this tire first. So it is said here in the tire that its radius is to be 0.35 meters. Okay, and let's say that for every rotation that this tire would be having, let's say that this tire is now to be rotating in one full rotation. For one full rotation, it means that the car would now be traveling its whole circumference. So with that guys, so let us solve for the circumference first. So the circumference is basically this subtended arc here, or the whole circumference of the tire. So circumference is once again to be equal to 2 pi r. So C is equal to 2 pi r. So substituting known values. So 2 pi times 0.35. So with that, our answer here is now to be equal to, so 2 times pi times 0.35. So this is to be equal to 7 over 10 pi, or 2.199. So it would be up to you on what value you would be using, but for a change, I would now be making use of this. So 2.199. So meters. So this is now to be the circumference of the tire. So it is now to be the whole distance here, or the whole circumference of the tire. Okay, the importance of us finding for the circumference is that for every one full rotation of this wheel, the wheel would now travel 2.199 meters. So from this point, he would now reach this point for one full rotation. And this distance here is to be equal to 2.199 meters per revolution, or per rotation. So what I am going to do now is that I will be converting this to rotations per minute first. Okay, so with that, so 3.15, so the acceleration is to be equal to 3.15 meters per second squared. So I want this to be in rotations per second squared. So times, so rotations per second squared. So with that, I want this to be converted to rotations. So with that, I want meters to be here, and I want rotations to be here. So in this case, as said in what we have been solving earlier, that for every one rotation, there is to be 2.199 meters. So with that, meters would now cancel out, and our answer here is now to be equal to, so 3.15 divided by 2.199. So our answer here is now to be 1.4325 rotations per second squared. So this is now to be the acceleration in terms of rotation. However, so if this is now to be its acceleration in terms of rotation, when we say angular acceleration, this must be in terms of radians. So this must be in terms of radians. So with that, I will be converting rotations into radians. So times we have learned earlier that for every rotation, so in one rotation, there is to be 2 pi radians. So rotations would now cancel out, and this is now to be equal to, so I will just be multiplying this by, so 1.4325 times 2 times pi. So basically, that is now to be 9 radians per second squared. So this is now to be our final answer in this problem. Okay, so if you're dealing with these kinds of problem, another shortcut is by using this method. So if you are now to convert from acceleration to angular acceleration, given these units, so angular acceleration is basically equal to acceleration divided by the radius of the tire. So shortcut. So if you would now be making use of this equation, so looking at the calculator, so 3.15 divided by, so the radius of the tire is to be 2.35. Thus, voila. So 9 radians per second. So there. So this is just to be a shortcut if you do not want to make use of this method. However, this shortcut is of course derived from this particular method. Okay, so there. Bye-bye.